Today I want to re-examine sodium aluminate in refractory acceleration. This presentation focuses only on refractory castables and gunning mixes. It does not discuss other industrial uses. The key message is simple. Sodium aluminate still works, but it is no longer the best default choice. In refractory applications, its safety risks, hidden costs, and long-term performance trade-offs have often been underestimated. So this review looks at the material through a more modern and more complete lens. Why review it now? Because the industry no longer judges an accelerator by speed alone. In the past, the main question was simple. How fast does it set? Today, that standard is too narrow. We also need to look at safety, environmental compliance, long-term durability, and total cost. A material that solves one short-term problem may create several long-term problems. That is why sodium aluminate needs to be evaluated under today's technical and management standards. In refractory practice, the risk of sodium aluminate depends on both the chemical itself and the way it is handled on site. It may be used as a powder or as a highly alkaline solution. In both forms, the core issue is the same. It is strongly alkaline and corrosive. During mixing, transfer, or nozzle injection, workers may be exposed through dust, splashes, or alkaline mist. So the site risk is not abstract. It comes directly from normal operating conditions. The chemistry explains why this material is difficult to control. When sodium aluminate meets water, it does not dissolve gently. It reacts quickly, releases heat, and drives the system to a very high alkalinity. In practice, that means rapid temperature rise, splash risk, and possible alkaline mist. If the material is added too fast, the reaction can become violent. There is also an important compatibility issue. It should not be mixed carelessly with acids or ammonium salts. So safe handling starts with respect for the chemistry. From a regulatory point of view, the message is clear. Sodium aluminate is not treated as an ordinary additive. Across major jurisdictions, it is handled as a corrosive hazardous chemical that affects transport, labeling, storage, documentation, and site controls. In China, it is also included in the hazardous chemicals catalog. So whether we look at domestic rules or international practice, the conclusion is consistent. This material requires formal management, not casual handling. To be fair, sodium aluminate became popular for good reasons. Historically, it solved real construction problems. It helped accelerate setting in cold conditions. It shortened demolding time in precast or castable work. And in gunning applications, it improved fast set and helped reduce rebound. So its widespread use did not come from misunderstanding alone. It came from real operational value, especially at a time when safer alternatives were less mature. However, being effective is not the same as being precise. In modern refractory systems, sodium aluminate often behaves like a row trigger, not a finely controlled accelerator. The useful dosage window is narrow. Too little and the mix is still slow. Slightly more, and the behavior becomes unstable. Too much and the system may flash set. It is also very sensitive to temperature, water, and mixing sequence. That makes process consistency difficult, especially in real production environments. The first hidden cost is extra alkali. When sodium aluminate is added, sodium is introduced into the system at the same time. For low alkali refractory formulations, this is not a minor detail. It changes the chemistry of the whole mix. Even a small addition can noticeably raise the total alkali level, and that extra sodium is added on top of what may already come from cement, aggregates, or other raw materials. So the real question is not only dosage. The real question is the total alkali budget of the formulation. The second hidden cost appears in the internal structure of the material. Under normal conditions, the hydration process develops a more balanced bond network. But when sodium aluminate drives acceleration too aggressively, that process can become uneven. Reaction products may form too fast and too locally. As a result, the matrix can become more porous and less uniform. That may look acceptable at very early age, but later it can weaken bond quality, reduce structural integrity, and hurt long-term stability. After drying and firing, the third hidden cost shows up at high temperature. In alumina-silica systems, sodium acts as a flux. In simple terms, it helps liquid phase form earlier than we want. That lowers the temperature at which the structure starts to soften. The consequences are serious. Hot strength can drop, creep resistance can worsen, and the lining may become more vulnerable to slag attack, thermal cycling, and structural damage. So the penalty of extra sodium directly affects service performance. The human risk profile also needs to be described accurately. This is not just a mild irritant. It is a corrosive material. If dust or mist is inhaled, it can damage the nose, throat, and respiratory tract. Repeated exposure may create longer-term health problems. On the skin, it can cause chemical burns. In the eyes, the damage can be severe and sometimes permanent. So the correct language is corrosive exposure, not simple discomfort. Most incidents involving sodium aluminate are not random. They usually follow clear and predictable pathways. One common case is splash during solution preparation, especially when solid material is added too quickly. Another is dust inhalation during open mixing. A third is leakage during storage or transport, especially when packaging fails or moisture gets in. Each scenario has a direct control measure: slow addition, continuous stirring, proper ventilation, face and respiratory protection, and reliable spill response are all basic requirements. The economic picture also changes once full compliance is included. At first glance, sodium aluminate may look inexpensive, but the purchase price is only the visible part of the cost. The larger hidden cost includes special storage, hazardous transport, personal protective equipment, ventilation, training, emergency facilities, waste handling, and potential accident liability. This is why the iceberg model matters. The material cost is only the small part above the waterline. The larger burden sits below it. In many cases, that hidden cost can outweigh the apparent saving. So what should its role be today? The answer is clear. Sodium aluminate should no longer be the routine default choice for standard formulations. The better principle is simple: do not use it unless there is a strong reason. For special cases, use should be conditional and tightly controlled, and only in real emergency situations, such as urgent low temperature repair with no good alternative, should it be considered acceptable. Even then, dosage should be minimized and safety controls must be fully in place. In conclusion, this review asks us to redefine what good acceleration means. Speed is important, but it is not enough. A modern accelerator must also support process stability, long-term performance, manageable cost, and strong safety compliance. The immediate task is to review any formulation that still uses sodium aluminate and evaluate its total alkali burden and operational risk. The strategic task is to move towards safer and more advanced accelerator systems. That is not only a safety upgrade, it is also a technical and commercial upgrade.